Hello. In this notebook, I'm going through the fundamentals of pytorch, starting from tensors, moving through tensor operations, and finally covering automatic differentiation with autograd. So this is the intro about the notebook. We are going to work on why pytorch. What we are going to learn is pytorch fundamentals, Einstein summation, autograd magic, from scratch primitives, high-level API, and complete training. We start with setup and imports. The notebook imports torch and torch NN along with functional utilities, data loader tools. It also imports NumPy and matplotlib. Then it prints the PyTorch version and checks whether CUDA is available, as you can see in the output. The output shows the PyTorch version, whether CUDA is true or false, the GPU name if available, and the device being used, either CPU or CUDA. This confirms where computations will learn. Coming to next part, tensor creation. Next, tensors are created from Python lists using torch.tensor. Just, yes. So Python list using torch.tensor, the shape and D type are printed to show the tensor dimensions and data types. Then a NumPy array is converted into a PyTorch tensor using torch.from underscore NumPy, as you can see here. The output confirms the tensor has the same value as the NumPy array. Yes. Here you can see both the values are float 64. Coming back, zero tensors, random normal tensors, and identity matrices are created using torch.zeros, torch.randn, and torch.I. The outputs display the actual tensor values and their shapes. Torch.arrange generates a sequence of numbers with a step size, and torch line space generates evenly spaced numbers over an interval. The printed output shows these generated sequences. In the third block, we have tensor data types. This section prints different tensor data types available in PyTorch. Then a float tensor is converted into int, float 16, and bool types. The output shows how values change. Float gets truncated when converted to integer, and non-zero values become true when converted to boolean, as you can see in the output. Then in the fourth block, we show the device management. A tensor is created on the CPU using torch.randn. It is then moved to the GPU using .to CUDA if CUDA is available. The output prints the device of the tensor to confirm it moved. Then it is moved back to CPU using .cpu and converted into a NumPy array using .numpy. The output confirms the conversion worked. Then comes the tensor operations. Two tensors are defined and element-wise operations are performed: addition, multiplication, and exponentiation. The output shows element-wise results. Matrix multiplication is performed using @ operator. And the output shows the matrix multiplication result, as you can see here. Transpose is done using .t and inverse is computed using torch.inverse. So these were the tensor operations. The output show the resulting scalar values. Then come reshaping and broadcasting. A tensor is reshaped using .view and .reshape. The output confirms the new dimensions, as you can see here. .unsqueeze adds a new line. Oh, sorry, not a new line, a new dimension. And .squeeze removes dimensions of size 1. Output shows how tensor shape changes, as you can see in the matrix. Broadcasting is demonstrated by adding a row vector or a column vector to a matrix. Output shows how PyTorch automatically expands dimensions, adding or removing dimensions. Then come the second part, Einstein summation. Torch dot E in sum is used to perform operations concisely. The INSUM output confirms that INSUM matches standard operation, batch matrix multiplication, and more complex operations are also shown. Output display resulting tensor shapes. Same dot products, outer products. We have batch operations. Cheat sheet. Then comes autograd basics. A tensor is created with requires underscore grad is equals to true. A function y is equals to x square plus 3x plus 1 is computed. When y dot backward is called, pytorch computes the derivative automatically. The output prints x dot grad, which equals 7 when x is 2. This matches the analytical derivative 2x plus 3 evaluated at x equals to 2. Computation graph visualization. Two tensors A and B are created with require underscore grad is equals to 2. They are multiplied, added, and squared step by step. When backward is called, pytorch computes gradients with respect to both A and B. The printed gradients match manual calculations. Gradients with vectors. A vector tensor with requires underscore grad is equals to true is defined. Loss is computed as the sum of squared elements. After backward is called, the gradient equals 2x for each element. And the output prints the gradient vector. Then we have gradients with matrices, important gradient patterns. Visualizing gradient descent. You can see the loss during gradient descent and gradient descent path visualization. In this gradient with matrices, a weighted matrix W is created with require underscore grad is equals to true. It multiplied with a vector and a loss is computed as the sum of squared outputs. Calling backward computes gradient for every element of W. And see the loss functions. In the end, this notebook walks through core PyTorch fundamentals, tensor creation, tensor mat, device handling, advanced operations with ENSUM, and automatic differentiation using AutoGrad. It builds the foundation needed to understand neural network training in PyTorch. This was all about this notebook. See you in next video.